Thanks, Matt. So just let me repeat that for the record. The Fourier series will turn periodic signals in time into a frequency representation. What's different from the Laplace transform is that the signal has to be repeating, and that means the signal was always existing for all time before you're looking at it and even after you're looking at it. Now, a long time really tends to be about 5 tau in reality, but things like repeating square waves, time-shifted square waves, sine waves, sawtooth, these are all signals that repeat. And the thing is you can turn anything into a signal that repeats. So let's just say you have a favorite song and you just have it on repeat, right? Well, now that your song is a repeating periodic signal, and you can take the Fourier transform, or take the Fourier series of it. All right. Now, whereas the Laplace transform, you took and found something in the time domain, in the frequency domain, that had a real and a complex part. The Fourier series and transform is all complex, and it means it's all sine waves and cosine waves. So everything it tends to have a discrete frequency instead of like a continuous frequency. All right. What it's great for is that you can find these frequency components that are really important in a signal, and then you can decide what to do with them. All right. But now, really, here are the equations, but it's really just like putting a signal into a prism and out pop the frequencies, and with a phase and a magnitude, or it's really, you have frequencies and it's broken up into a cosine and a sine wave, and what you're finding are these constants, right? And sometimes the constants are negative, sometimes they're positive, and sometimes they don't exist, all right? But the first thing you need to do is find out what the period is so that you can find omega naught. And then these first constants are really just a DC offset, and that might be 0, or it might be negative, it might be positive. And then you have this infinite sum of sines and cosines. Now, if you combine them into one cosine wave, right, it's just a cosine wave with a phase, or you can even use the exponential representation. We tend to stick with these two in this class, although I believe 112 likes this definition. So that's really the summary. I know it's like I said, it's like a prism. You add these harmonics to a fundamental frequency. So yeah, I guess the big ideas are what you might call simple, or there's not a lot to know, but then the application and the finding of it, that's where it gets fun. Okay. So let's just do an example of a sine wave. Now, if I do a sine wave and I want to represent that as an infinite sum of sine waves and cosine waves, well, really, there should only be one sine wave. So I already know the answer. I should be able to do this one in my head. So x of t is the signal in question. All right, we given an omega naught. And then we find the DC offset A naught. So that's 1 over T naught And we take the integral to the period, and turns out that it's 0, right? Because, you know, a sine wave or a cosine wave with a DC offset is 0, you take the average of that over the period, right? It's going to be 0. Then when we look at the A1, right, we have a sine times the cosine, and when we work that through, we get 0, right? Because there's a sine wave, there's only one sine wave. This is xt. So that means everything else should be 0. Then when I look at B1, now I'm multiplying things times sine waves. And here's something, right? Notice the frequencies are the same. This is really sine squared, right? So now, right, if you're finding the integral of sine squared, well, it really should be non-zero, right? It's almost like a full wave rectifier. And it turns out that we get 1, right? So what does that 1 mean? That means it's this sine here is multiplied by 1. And so that B1 is really 1 times the original, this frequency. Does it exist at other frequencies? Well, you find out that it's 0. Yeah, Nick, actually this PowerPoint should be posted already. It just might not be the first PowerPoint. Oh, never mind. Okay, sorry. So really the big thing, right, is that if I want to represent a sine wave as an infinite series of sines and cosines, well, really there should only be one sine wave that comes out, right? And again, it didn't have a DC offset, right? But what you're going to find is that these, notice it's 1 over the period, integrating to the period something, right? And that's the original thing. So if you can just look at that and see that there's a DC offset, right, you can almost do it in your head. Notice now we have 2 divided by the period, integrating over a period, and now we're multiplying 2 things by each other, right? Just let me finish my thought, Har Sarup, and then I'll answer your question. But now look here. Something, a number, happens to be 2, divided by the period, integrating over the period, and then we have a function times a function, turns out to be the same. So really that's like x squared. And if I got rid of this 2 and took the square root of this, I'd have RMS, right? And so while we're not really finding RMS, if you take the integral and scale it by 1 over the period and then integrate over the period, you're finding the average, right? That's, oops. I had something running in the background. Sorry about that. And so we're going to see is that when you look at one of these plots, sine squared, it has a non-zero average. Everything else has a 0 average, and that's why it's 0. But in some ways, it's very, very similar to finding RMS. Now, to get to your question, no, actually it doesn't. It works for anything. If you can imagine it, we can take the Fourier series of it. Now, and we're going to do some non-continuous. So Danielle, I think you're asking why is the 2 here and why is the 1 here? Because this is the DC average. That is the definition. Now, why are we multiplying it by 2? Because if you didn't, you'd get the wrong answer. I mean, this is the definition of a Fourier series. And if you don't multiply it by 2, right? I'd get 0.5 when the original sine wave had an amplitude of 1. Okay, that's a great question. So the book has these various ones all worked out. All right. But like, how would this be used? I'm just going to give you some, overarching case studies. And so what this circuit does is ultimately measure your heart rate. Now, it's supposed to take an infrared sensor, you put your finger on it, and it amplifies and filters and, blinks an LED, right? But the signal, which this is basically a signal that I looked at real data and then made a signal like it. So the first thing you have to do when analyzing it is find the period, which is 1 second, right? So it repeats about every 1 second, because your heart rate isn't exactly the same. But so that means we are at 1 hertz. So the period is 1. So that means we can build this up into a series of sines and cosines. And yeah, this is a reverse triangle wave with noise added, right? So if I put this into the Fourier transform, I should get a very strong, there will be a DC average, right? Because notice it's only going from 1.702 to 1.712. And the signal's really small. That's why you need an amplifier. But we're trying to get rid of this noise. All right. So this is the fast Fourier transform that you can do in LTSpice. Where did the DC go? LTSpice gets rid of it. All right. And this is that fundamental frequency that if it's shifting around, that's your heartbeat. All these come along with it. These are all sine waves with various magnitudes, sines and cosines that you have to add up to make the original signal. And so if I just draw a box around it, that's like a bandpass. That means I'm trying to get that signal. And in this case, the rest is noise. We can even look at this in terms of a half-wave rectifier, right? Where you put a sine wave and you had a diode and it only let half through, right? Well, here's V in, the original signal. And then this signal is a half-wave rectifier. I didn't use a diode, I programmed it because I didn't want to deal with the non-idealities, all right? So this sine wave is the input, and at 60 hertz, right, there is a magnitude there. And the rest of this, this isn't real information. It's just an artifact of the fact we're doing a digital simulation, right? Then I do this half-wave rectified. Well, now it's no longer a pure sine wave like it used to be. And so the original frequency is there, but then I've added some other frequencies, and that's really there. And then I do a low pass filter, right? Because I want to keep the DC part. The DC part is over here, and like I said, LTSpice removes it from the Fourier transform results. All right, so this is coming out. These are the parts I want to get rid of. I put it in through one filter and I reduce it, right? It's a little bit below 0 dB. Put it through another filter and then it's a whole lot less than a dB. And so ultimately I want a DC signal, right? That's what these converters do. So here's a sine wave. Here's the half wave rectified. Here's from one filter. notice it goes from 0.8 to 1.2, right? So there's still some, there's still a time varying signal in there, but it never goes below 0.18, right? Then I put it through the next filter, and even though it looks like, oh, the sine wave has totally come back, look, it's swinging between 1.01 and 0.987. So if I were to plot this, right, and it's centered around 0.999. So I'm getting 1 volt, and there's something called a ripple, all right? That's what you were really doing in your 97 and lab. And most, if you've had a circuits lab, which you should have, almost everyone does a diode rectifier type thing, okay? And that's really all I wanna. So the first spec is. Right, this 60 hertz is a 60 hertz sine wave. I had it going the magnitude, probably I was coming up with some random number. But yeah, this is the actual frequency. And notice it never really goes away, but if you look at the first, right, its amplitude is reduced quite a bit. Then if I look at it again, it's reduced even more. If I were to plot this on a linear scale, it'd be a lot harder to see the ones without the ripple. I guess I didn't put a file name under it. So these repeated spikes, right, come about because while one sine wave might be able to represent one sine wave, you need an infinite sum of sines and cosines to represent this kind of shape, which you can see is not, it's not one sine wave. It's made up of many, many shapes. And so that is a result of this half wave rectifying thing. Okay. So now notice, this is sine squared, right? It doesn't go below 0. And you can see that the average is no longer 0. So there is a DC offset, which you would have to find on your own. LTSpice won't calculate it for you. Although you could do a measurement script that would do it for you, but the FFT doesn't. And so what you can see, right, is that there is one peak, and it's actually at twice the frequency, where it was where the original sine wave before I squared it went from 1 to -1 in 1 second. Notice how the period is changed, right? So it's actually twice as fast. And then what I meant by seeing, you can look at things on a linear scale, and then you can see the most important part. Okay. All right. Just to let's just do it just so we can visualize it. And so this is just the square of the other. So then if I looked at here's the original sine wave with no DC offset. Here's the squared sine wave, doubles the frequency, right? The DC offset isn't shown. And then if you want to see it on a linear scale, you can see what happens. Okay. But those are, yeah, really good questions and comments. So like I said before, any periodic signal can be broken up, right, into a DC offset, which may be equal to 0, and sines and cosines, or cosines with a phase. So again, the way we find these is the offset is just the average of the signal. All the AN constants are the average of the signal times cosine, and N is frequency 1, 2, 3, 4, right? So everything's discrete. And then the BNs are the original signal times the cosine. And again, N equaling 1, 2, 3, 4. So it's really important to get the period right. So if we have a pulse train, right, where, right, it's not continuous. So it's going to be 2 when time is between 0 and t divided by 2, and it's going to be 0 for when time is between these values. All right. So it's basically the amplitude is 2 and it's on for half the time. That's 50% duty cycle. But this is a square wave, right? So it's either going to be 2 constant or 0. So here's our original setup, right? Between 0 and the period divided by 2, it's 2 plus 0. So we just ignore that. We go through and we get 1, right? Because the average of that signal would be 1. All right. Then we do the ANs, right? And we go for, since this part is always 0, I'm going to, for the rest of the example, I'm only going to go between 0 and half the period, right? So I have 2, right? That's the original signal times cosine, right? And I work it through, and it turns out that no matter what n is, it's 0. Okay. Then to find the b constants, right? I've already know not to integrate from half the period to the full period because that's 0. So I'm multiplying by sine, and n is just harmonics of the original frequency, right? Work through the math, and you get 4 divided by n pi. All right. But not only that, it's n has to be odd, but it's also 0 if n is 0. I mean, it's 0 if n is even. If you go through these examples, you can see. All right. So that's So here we have a signal, right? And it looks like sine waves are in there, right? And you might see that there's a period to it, but it's a little bit difficult, I think, just to look at it and see. And all I've done is done a linear sum of some sine waves with various amplitudes and frequencies. So the thing that's great about the Fourier transform is that it can take something that's kind of hard to see in the time domain, right? And if I split it up, right, you can see that there's the various magnitudes are back at the various frequencies, right? And but if you were thinking, let me make an actual signal that actually sums these. Okay. So this is the actual, I've summed it, right? So now if I do the fast Fourier transform of that, you can see the peaks are there, right? I can put it in a linear, and you can see I have something at a hertz, something at 3 hertz, something at 2, 7, and something at 10. So you can see that it might be hard to see what's going on here, right? But put it through the prism of that algorithm, and out pops all those things. Any questions so far? So if we so the period, right, we can put dots to say that it's always doing this, right? The period is 1, right? We can see that it's repeating in 1. So the frequency is 1 hertz, and omega naught is 2 pi times f. All right. So that means that this is that fundamental frequency, and no matter what is going on, I could have a 0 DC offset, but no matter what, those fundamental frequencies or those harmonics are going to be n omega naught, which means I can have something here, 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 right? But nothing in between. Now, if I change the frequency of this to a half, or the period to a half, right, then it will move these around. All right. So A0, right, the DC part, and here's the equation. Right? But really, right, I mean, you have 1/2 the base times the height. And so the base is 1 second, and the height was 1. All right. And so, you know, just by finding the area and dividing it by the period, right, will give me the DC average, right? So hopefully you can see how the DC average is going to work, right? Yeah, Matthew, I went a bit quickly with that, but yeah. So in this case, right, the period is 1 millisecond. Right. So And you can see that, you know, yeah, I scale it by 1 over T naught, but I'm integrating over that, right? I'm still going to get one half. And this was something when I first was, you know, I can kind of remember struggling with RMS, right? Is that, how is it that a 1 kilohertz, 1 volt peak, right, amplitude, had the same RMS as a 10 kilohertz or a 10 hertz or whatever. But as long as the amplitude was the same, the RMS was the same, right? And that's because even though, yep, we're taking the square root, everything is 1 over T naught. And then you just had this relationship. But because of this, right, it didn't matter. Now, yeah, something to, maybe it's a good time to just sow a little bit of gotcha. So I'm going for 5 seconds, right? That's a 1 hertz sine wave. So if I'm going to, I can use LTSpice just to find the average by doing a control left click on the signal in question. And it's giving me, the average is 0. Nanovolts is effectively 0, right? And it's giving me the RMS, which is what I would expect, right? But now what I'm going to do is keep the amplitudes the same. So the amplitudes are the same. The RMS is near this, practically the same, but the average will be a little bit off. Because if I, oh, notice how the signal's coming up, but when it ends, it's coming down. So I'm not really averaging, oops. Over the proper, that area should be like 0, right? But it's not quite right. And so if I, this can be better seen if I do a pulse.
Your V2 source only has 3
Yeah.
parameters.
I was, thank you, just about to think that I was. All right, everything else is annoying me. That's not right. Okay. So now, right, I want the average of that. That will give me 500, right, or 0.5, because that's a square wave and it's a half, right? If I wanted, if this were on for 75% of the time, right, that would give me the average. But if I'm simulating, right, this is a 1 Hertz square wave. What if I don't simulate it for the right amount of time? So, see how the average is not correct? It's because when I did the simulation, it's on a little, it's not a nice period spacing. So when it's integrating for a little bit longer than it should. And so everything else is off. So it's just something, if you want to look at you're trying to check your work, right? Just to make sure you have to get the period right. So if I went up by a half a second, I was on for 0 in the period, right? So now I'm only on for half the time, right? So the average is 0.3, right? But if I took a second to rise, oops, violated my own rules. There, that's 2 periods. So that's what we calculated before, right? 2 periods. Let's just go back. .25, that makes a lot more sense. All right. And then if we said the rise time was milli and we were on for milli, so now let's simulate for 2 milli. We get the same answer. You almost might not have noticed that the axis changed down here. Okay. But you even saw myself make the mistake of not setting up the simulation into whole numbers of the period in question. And we can even see the Fourier. All right, so there's our first peak. And this is actually the transform. You have a peak at every harmonic. So 1 kilohertz, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which is why triangle waves like this can be used in synthesizers. Where it looks more like that. Okay. And what you do is to, like a piano or a guitar, it might be having the bass note, kilohertz, but then what makes it a guitar or a piano or a drum is these harmonics. And depending on the instrument, right, some of these harmonics are there or they're not there, right? So you either filter them out to make the sound you want, or this is a way to generate sine waves at various frequencies, which then you can add together. That's just another way of doing it. Okay. But if you all right, look at the homework, right? The first part is finding the DC average in the period. And when I talked to Professor Morelos, who teaches 160, he says that's a lot of what you need to remember from 110 is to, or it's done quite a bit. It's just you have to be careful, right? If I look, it's going from -1 to 1. It looks like it's the same thing, but it's not going to -1 anymore, right? Here you can see the squared function. Here's a pulse that's on for probably a quarter of the time, half, 3/4. And so, yeah, in some ways we've kind of done that bit already. And then when I said I'm talking about music generation, that's problem 6. But really, you just have to find the transform. All right. Then another type of problem is I give you the transfer function. I mean, I give you the expansion, right? And then you have to say which one it was, right? So hey, there's a DC component here. All right, which ones have DC components? Right? This one doesn't have a DC component. All right, which ones don't have it? So it's just like a game of logic, okay? But yeah, you probably could do 7. Oops. Probably do, when I say what kind of filter, right? High, low, notch, band. And then number 1 you could do right now. I know. Subtlety is my middle name. So now there's now the thing is I know a lot, you know, almost everyone can kind of do a plug and chug, right? Well, let's call this sine 2 pi t squared. All right. So it's squared. So the original frequency, the original period would have been 1 second. Now it's doubled. We'll just call that 1 and call that about 0.5. Now, intuitively, or just kind of drawing pictures, you know, let's see if we can do this. All right. So A naught is the DC average, right? So if I were to, I'm trying to break this up into trapezoids, right? All right, I could find the area under each trapezoid and manipulate it that way. But the thing is I could do one rectangle, right? And notice that in here, that rectangle is too big, right? That's my error. And then over here, my rectangle is still, it's too big, and that's the error. And then here, my rectangle is too small, and that's the error. Now, yeah, if I draw my rectangle properly, right, the error that's too big would equal the error that's too small, and then the errors would cancel out. And so, right, that rectangle is going to be 0.5 long. If I have it 0.5 high, right, I'm going to get 0.25. So let's just say T naught in this new case is 0.5. And that's, you know, my A naught. Now, what I'm saying to do here, right, is that's the original signal, but this is the signal that's multiplied by a cosine at frequency 1. This is it multiplied by the cosine at frequency 2, cosine frequency 3, cosine frequency 4, right? Sine frequency 1, sine frequency 2, 3, and 4. And just by kind of doing that error, like you can tell, this looks like, you know, it's like goes up to 2, down to 2. The area is going to be 0, right? Here, I can definitely see that the area is not going to be 0. Here, I have to kind of do it out. And because I forget the answer, I have to go and do it. But you can just tell very easily if an area is 0. So if I drew a line across this, I'm not quite sure what's going on with that shape, but I can tell that the area is 0, right? If I drew a line halfway across here, yeah, it probably looks like I have 1 up, 1 down, 2 down, 1 up, areas cancel. All right, so I could do by eye the Fourier transform, at least when it's 0, right? And on exams, I have you do this and you show your work. Yep, you can use Python, you can use all these things, but this really shows that you're getting what's going on, which is the average. So if you look at all these sine waves, the amplitudes are 2, the frequency is set to 1 hertz, right? And frequency 1 is 1 hertz, frequency 2 is 2, 3, and 4. So those are the first 4 harmonics, right? Some are multiplied by sines, some are multiplied by cosines, which is, I have a phase difference there. That's how I get cosine in LTSpice. And so you are finding the A and B constants just by doing this kind of thing. Okay, I'm just, and sure, you're not going to get the exact value, but I can tell if something is 0, positive, or negative, and that tends to be how they're graded, right? It canceled, the average canceled out. The average was positive. The average was negative. Okay. Now, notice, and it's also the definition. This is the xt, so finding the average of xt by itself is an. All of these are the original signal times a cosine. So that's going to give me a1, 2, 3, and 4, right? This is the same signal multiplied by the sine waves, right? But a frequency 1, 2, 3, 4. So this is going to give me B 1, 2, 3, 4, right? Sometimes people get confused that they think each one is a separate Fourier expansion to find. No, I'm just multiplying it out so that you can see that really you're just finding 2 times the average. Either it's time of the original signal times a cosine or times a sine. So it's really the definition of the Fourier expansion. Okay. So this is a whole lot of what I might call ugly Python code. I'm calling it saw wave, but really, if the X, like there's a duty cycle, and if the duty cycle is greater than some, it's 0 or it's 1, depending on where you're at. This is set up to be 50% duty cycle. And so it goes through all the code of finding the A and B constants and then plotting them and then actually finding the phase. So remember I said everything was in terms of sines and cosines. So, but this is now in terms of C, which is a sine wave, which is the magnitude, right? A 50% duty cycle pulse, which is what it was, has a DC offset of 0.5. But then C1, right, that first coefficient of that first sine wave at 1, here I'm saying kilohertz. Now, here I'm going to give you maybe a little hint. In here, notice I just have T naught, right? But notice I'm giving the frequency is like 1, right? And all I'm doing in changing this, right? I calculated for a frequency of 1, changed the plot dimensions to be kilohertz, and it's the same thing, right? Just a little tip. And then the phases are all minus 90. all right? Which means that this is really a series of sine waves. Because if the phase was anything but minus 90, or if the phase were 0, it'd all be cosines, right? And you can see that now it's going between the odd frequencies. So the thing is right, this is always repeating, right? And what does a sine wave look like, right? It looks like this. What does a cosine look like? Which I have a real trouble with cosine, right? It looks like this. So yeah, you can see that this has its 50% duty cycle, and if that's 1 volt, right, it's going to be A naught is 1/2 almost by inspection, right? We know that the fundamental frequency will be a sine wave, right? Or a cosine wave, but it'll have right, n is 1, 2, 3, 4. So n equaling 1 is the first sine wave, right? And it's got a period. So I'm going to try to draw this a little bigger. So now I'm going to try to draw, just A naught equals 1/2, right? I'm saying that the sine wave looks like it'll be a better fit than the cosine. So I'm just assuming all the A n's equal 0. So let me just try to draw, right? Let me just try to draw a sine wave. Right? And so if this is a half, right, it's going up by a quarter and down by a quarter. So that'd be right. And you can see that in here, the error is too small. The error is bigger. Here, the error is negative in comparison and negative in comparison. Now, you might think that I was just able to find the first coefficient as 0.25. But the thing is the whole, when you start summing these, you're actually going to get oops, this kind of shape. And when you start summing these together, the 0.25 isn't right. But what I'm saying is you can see that that shape fits better than the cosine shape. All right, that a sine wave fits in better than a cosine wave, which was all I was trying to say. Next time, what we'll do is, now that we kind of have intuitively what we're doing, you know, go through and formally derive more of these expansions. Okay. All right, that's it for today. You know, the appointments are there. I think the people are happy to go there. But it seems there was an initial rush and now they're kind of empty. Take care. Bye.